Today's video is electron properties or quantum field effects. And this goes along with my recent video, proton properties or quantum field effects. And you were probably taught that electrons are point particles or point-like particles. But the thing is, the quantum field exists, and we know from the Casimir force, which is due to van der Waals forces, which require dipoles, that the quantum field is composed of dipoles. So dipoles are going to be polarized around an electron. There's nothing we can do about that. So whatever structure an electron has is ultimately going to be due to what happens with these quantum dipoles that organize themselves around an electron. And we know that there's a structure to it because of the magnetic moment. And if you're familiar with the magnetic moment calculation, it's minus g over Es divided by 2 times the mass of the electron. And in this case, S is h bar over 2 Planck's constant, the reduced Planck's constant divided by 2. Well, what they often don't tell you is using mass in this equation is disguising the fact that we're really using the Compton wavelength as the dimension. Because when you calculate magnetic moment, you need to know the charge, you need to know the radius, and you need to know the velocity. So if we reorganize the equation, that's what we get. We get G times E times c, the speed of light, times the Compton wavelength, divided by 8 pi, where that's a geometrical term. 2 of that is just you divide the Compton wavelength by 2 to get the radius. So we've always been using the Compton radius as the radius of the electron, even though you may not have been taught that. It's always been a hidden assumption. And so that tells us that we have a shell that's rotating at the speed of light. But it's made of electric charge dipoles. So it's actually 2 charges that are rotating in opposite directions. And that's why the G factor G is approximately 2, because instead of using a single shell with a single charge rotating as an approximation, we really need to consider 2 shells that are nested, rotating in opposite directions, each contributing an equal amount to the magnetic moment, giving us a factor of 2. Now there's correction terms because it's not exactly a factor of 2 due to the electron self-energy and some other issues. But that tells us that there is a real structure at this radius. And another important thing to note is that we have to look at where does this speed of light spin come from. And that's because you can't have polarization without rotation. When an electric charge moves, quantum dipoles will rotate in relation to the charge. So there's rotation anytime you have a charge. Not only that, since quantum fluctuations are constantly popping into existence and going away, you have a constant reorganization of charge dipoles around an electron. And the thing is that if you have an orientation where, say, they start this way, and you have a charge here, they would have to turn inward, which means the like charges have to come together. And if it's more extreme the other way, and they have to rotate like that, then you also have like charges coming together. And that requires energy. Or you have to have the whole dipole move, which also requires energy. The way that it requires the least energy for polarization to occur is if the dipoles rotate together in the same direction. That requires the least energy. So that's what nature does. So the polarization causes rotation. And it causes an organized rotation around the electron. So that creates spin. So spin is a natural process of the rotation that occurs due to the polarization of the quantum dipoles. Spin is not a property of the electron itself. Just like magnetic moment is not a property of the electron itself. It's a property of the quantum field. And so that gives us our second thing. We have spin and magnetic moment. Then we can look at the charge. Where does the charge magnitude come from? Well, to get that, we have to think about Gauss's law, that E equals surface integral of P, the polarization flux, dot dA, the area. And which tells us that if you integrate over any area, consider a sphere most simply, that whatever size sphere you have around the area, it has the same amount of charge. And this is necessary for the inverse square law to be true. And we are taught then that the amount of flux is due to the amount of charge, which gives us the charge magnitude. And when you're adding up multiple charges, where you have Q and you have many, many electrons, and you sum up the total charge, they do relate back that way. But that's not what's really going on. Because we have to consider that when we're looking at a field of dipoles, dipoles rotate, cause other dipoles to rotate, which cause other dipoles to rotate. And by their nature, the dipoles don't want to rotate because all the other dipoles are resisting their rotation. And this resistance takes the form of the quantum van der Waals torque. And that's why we have two main constants. We have permittivity and permeability, which are the resistance to polarization and resistance to magnetization, which are both due to quantum van der Waals torque effects. And it's this resistance to polarization that determines the polarization flux. The amount of polarization we get from a polarizer is limited and regulated by the quantum field, not the charge itself. So the basic magnitude of the electric charge of a single electron is due to the polarizability of the quantum field, not the amount of charge that varies sprinkled on an electron. So here, again, we have charge magnitude being due to quantum field effects, not a property of the electron itself, what I call a bare electron in the center. Then the next property considers mass, and I've done a video on just this alone, I'll link below. If we consider that we have a shell of quantum fluctuations, that shell is going to eliminate quantum fluctuations that have a wavelength equal to the diameter of the shell. And if you use the energy density equation for the quantum field for the wavelengths of a nominal thickness shell of this type of structure, we find that the electron's mass is equal to the 0 point energy excluded by a Compton wavelength diameter shell. So the shell that's necessary to get the magnetic moment that we know is real also gives us the mass of the electron. And then in addition to this, we have charges around an electron are also electron-positron charges. They're organized with respect to both matter and antimatter, in addition to electric and positive charge. And because of that, the quantum field also gives us the matter-antimatter orientation of the particle. For an electron, it would say matter facing out, and for a positron antimatter. And so we also get the antimatter properties being propagated through the quantum field from this quantum field shell. I also skipped over when I was talking about the rotation. Note that the rotation is c, the speed of light. That means that these dipoles, when they rotate, have a tip speed around the equator equal to the speed of light. And so, of course, they can't go faster because they're regulated by the rest of the quantum field. So the electron can't get bigger, because if it got bigger and was rotating at the same rate, it would exceed the speed of light. The speed of light, the tip speed, caps the structure, so that we can think about the polarization of the quantum field polarizing at a certain rate until it reaches the speed of light limit, and then it can't grow anymore polarizing at the same rate of rotation. It has to stop. And that's what sets the size of the shell. That's what gives us the size of the electron. And note that with a proton, this polarization rate is different. When you have a positive charge and matter, it's a different polarization rate, higher polarization rate, than a negative charge and matter. And that relates to something going on between charges and matter that I haven't worked out in detail yet. It's one of the most fundamental questions in physics that needs to be answered, is how are electric charge and matter and antimatter related. But in general, all these things that I've said about an electron are also true with a proton, except the proton's radius is its charge radius that we know experimentally from scattering experiments. And we've already known or seriously suspected that the structure at the charge radius of the proton is made of polarized quantum fluctuations. So exactly the same situation. So electrons and protons are the same type of particle, or potentially the same particle, depending on how you want to define it. Anyway, I hope you enjoyed this video on how electron properties are quantum field effects and have learned a little bit more about what an electron really is. It's really a bare electron in the middle that polarizes with respect to electric charge and matter-antimatter orientation. And all the other basic properties of the electron are quantum field effects. And it's a quantum field that gives us those properties. So if you like this video, please like it, share it with your physicist friends, and subscribe to see more of my videos in the future. And if you'd like to study this more, I have a book, Goodbye Quarks, the Onium Theory, that talks about proton-electron structure and also onium structure of higher energy resonances. So basically we can completely replace the quark model. And then on my basic quantum field theory research, I have the 0-point universe and the 100 greatest lies in physics that are also available. And I'm a retired independent researcher, and if you buy a book, it helps me in my retirement, and I also have a Patreon account, and that helps me to make more videos and to do more research. So thanks for watching, and thanks for your support.